this is the first case and the behavior in the first case. Now in for, for the second case, which the code mentions as the first case, then what does the code say for the second case? The limiting value of the moment of resistance of the section may be obtained by the following equation when df by d does not exceed 0.2, uh, when df by d. Now, let me first explain to you what is d here and what is df. I told you already you have this as the, now this is your d now, right from this point up till the center of this is your d, small d. Now, when your xu is greater than, this is a case when your xu is greater than, if xu is greater than, when your xu is greater than df, जैसे कि इस केस में है your xu is greater than df, then what do you have? In case 1 there will be two more cases. Df by d, what the code mentions, df by d does not exceed 0.2, that's it's less than or equal to 0.2. The ratio of df by d, that's df is 20% of effective depth d. तो उस केस में what do you have to do? Your mu is given by this equation. Now, if you recall, this mu is equal to 0.36 xu max by d, 1 minus 0.42 xu max by d, fck bw d square. What is this? This is the, you already had this equation here, this. तो यहाँ पर ये repeat हो रही है this equation. But only thing which is changing is that there is bw here in this case. This is bw. Now what is bw? bw is, I'll show you. This is the width of section. This is bw from this point till this point, means from here up till this is the width of the web. I told you that this is bf here, this is df, and then there will be dw as well, which will be the depth of the web. From this point up till the bottom of this b, it will be dw. Now if you want to take the effective width of the depth, then it will be from this point up till this point. That will be small dw. Now what does the code then say about what is the equation that you have to take? the equation that you have to take is this one. So let me copy paste this here. Now your equation is this in the case of df by d less than or equal to 0.2. For df by d less than or equal to 0.2. So what does this mean? This means, number one, you have only this much portion. So, number one, you have this portion. ऐसे करो and define इसको this portion. It's number one, this is behaving in compression. तो उसका इफेक्ट यहाँ पर लिया गया है. The effect of that portion is taken into consideration here. Next, you have this portion in compression, which is the part of the flange. So, तो वहां पर क्या लिया गया है? What has been taken कि ये जब BW लिया गया है and D, क्योंकि D will be taken from the top, so it has been divided into, number one, this portion is in compression, and then rest this portion and this portion is in compression. तो इक्वेशन को ऐसे डिवाइड किया गया है, this is 1 and this is 2. तो ये पोर्शन फ्रॉम this portion, it defines the compression behavior of this rectangular portion, this one. And the second, this one defines of, number one, this, the part of the flange left, and of this. So this we know, this ये हमें पता है from the rectangular behavior. इसका हमें पता है part 1. Now part 2, इसका behavior कैसे पता चल रहा है? BF minus BW. What is BF minus BW? BF is total, this all, right from here up till here, and BW is this portion. So what is left is this and this, if you do BF minus BW. So into DF ये है. What does it give you? It gives you the area of the section which is in compression. Then D minus DF by 2. Now D minus DF by 2 is giving you the lever arm, which would be taken for lever arm for this portion, which would be at the center of this. So it's D minus DF by 2 is the lever arm. So you're then getting the moments into the stress, which is 0.45 FCK. अगर if you recall, जब हमने stresses निकाले, we had 0.447 FCK as the maximum compressive stresses. So that this is 0.447 FCK or 0.45 FCK. ये वहां से आ रहा है. Because for this portion, the behavior would be uniform. The stress behavior in this portion would be uniform. और बाकी portion में it's then assumed कि यहाँ पर the rest of the portion would be non-linear. So for this portion, it's assumed that behavior is linear. Only when your df by d is less than or equal to 0.2, then it's assumed that this portion behaves linearly. Thereby, it's 0.447 FCK or 0.45 FCK. तो ये equation बनती है once you have df by d less than or equal to 0.2. Then next is if you now have df by d exceeding point 2, the moment of resistance of the section may be calculated by the following equation. Mu is 0.36 xu max by d. This is. So let me again copy paste this. Your df by d exceeding point 2, the moment of resistance of the section may be calculated by the following equation. 0.36 xu max by d, 1 minus 0.42 xu max by d, 0.1 fck bw d square. Now, you would say, what is this? Let me again redraw this. Now your section is somewhat like this. It's up till this point. Your df is now this. Once the code says once its df by d is greater than 0.2, what happens is that the part of this stress block in compression no longer remains in only linear. So the behavior is not only linear. The neutral axis would be somewhere here. Now, if you check up till this point, it's linear. And then, so this much portion is in nonlinear, and this much portion is in linear zone of the flange. Then all of the portion of this web uh, above the neutral axis is in nonlinear zone of the stress block, and this would be in tension. So what does the code do? It says it puts up a new term yf, where yf is 0.15 xu plus 0.65 df, but not greater than df, and the other symbols are same as in g11 and g12. So it puts up a new term. So this portion was for the flange. This portion was for the flange, but now it will be only this much portion of the flange. जो ये blue में यहाँ पर ये portion आ रहा है flange का, it would be only that much portion, and its depth would be yf. Its depth would be yf from here, top, till this point. Or yf, how would you get it? 0.15 xu. So you know what is xu. This is xu from this location up till this point is xu plus 0.65 df, and this is df. This total is df right from here up till this point is df. So you can get yf. So now you're only replacing जो इससे पहले वाली ये इक्वेशन थी, this one, here you were using the whole df to be in the linear portion or uniform stress portion. But once df gets greater than 2.2 times d, then only half of the portion of the flange is in the half of the portion of the flange is now in the linear portion or the uniform portion. और उसको हम the code mentions it, you can calculate it by yf equal to 0.15 xu plus 0.65 df. So then this equation is accordingly changed. The rest of the portion is same. This 0.36 xu max 1 minus this is already there as you have it here. So and there is no other change now, but there is a clause here that your yf should not be greater than df, and the other symbols are same. Obviously your yf here would not be greater than df. Now there could be a case, any other case, where xu max is greater than xu is greater than d. The moment of resistance may be calculated by the equation g.2.2, which you already had in the code. Let me show you that. This one, which was meant for your df by d does when it's not exceeding zero point 0.2, when your whole flange is in compression and it's in linear compression. Then when your xu max by is greater than xu is greater than df, the moment of resistance can be calculated by the same equation when df by xu does not exceed 0.43, and this uh, g2, then the second clause is that you can take from the second one, this df by d not exceeding 0.2, exceeding zero point 0.2, when your df by xu exceeds 0.543. In both cases, substituting xu max by xu. So this equation it would be used जब हम limiting moments इसमें निकालते हैं. So how would you now go for design here for of a T beam? Anyone has any questions up till this point? Yes, anyone has any question? 've taken this question from a book. 58. You're writing on the screen. The question is, a continuous T-beam has a cross-sectional dimension shown in this figure. I'll show you that. The web dimensions have been determined from the consideration of negative moment at the support and the shear strength requirements. The span is 10 meter. This is 10 meter. And then you have, and the design moment at midspan under factored load is 800. This is not watt meter, kilonewton meter. This factored load is 800 kilonewton meter. So it's already given in the moments. The moments are given. Determine the flexural reinforcement requirement at midspan. Consider Fe415 steel, and assume that the beam is subjected to moderate exposure conditions. So this is the question that we'll be doing, and your beam dimensions are, this is 1500. This is, what is this? BF is 1500 meter. How much is DF? This is 100. Not meter, this is mm. And then your BW is 300. This is your BW from here up till this point. And total D is 700 mm. Is it not D? Overall D, that's capital D, is 700 mm, which is from this point up till the bottom of this. Now, obviously, this would be at the center of this. ये जो rectangular portion है of the web, it would be at the center of the flange. Now, how did he get that this BF is 1500 mm in the question? How did he assume that the effective width of the flange is 1500 mm? It's again given in the code. It's page number 36. This is T beam and L beams. A slab which is assumed to act as compression flange of a T beam or a L beam shall satisfy the following. The slab shall be cast integrally with the web, जो कि मैंने कहा. Web and flange of the slab should be cast together, or the web and the slab shall be effectively bonded together in any other manner. That's first thing. And second thing is, if the main reinforcement of the slab is parallel to the beam, transverse reinforcement shall be provided as in figure 3. Now, जो मैंने कहा कि there is a bar, this is a bar here. This is the bar that's cast in the slab, and so the transverse main reinforcement of the slab is parallel to the beam. Transverse reinforcement shall be provided as shown there. Such reinforcement shall not be less than 60% of the main reinforcement at midspan of the slab. तो ये reinforcement जो provide करनी है, it should not be less than 60% of the reinforcement provided at the midspan of the slab. जब हम slab करेंगे, then you will come to understand how do you provide the main reinforcement of the slab, which is the tension reinforcement of the slab, like you have in the beam. जैसे यहाँ पर tension reinforcement provide करते हैं, similarly slab में भी provide करते हैं. Then effective width of the flange, जिसकी मैं बात कर रहा था, in the absence of more accurate determination, the effective width of the flange may be taken as follows. Now you don't know, आपने slab और beam को इकट्ठे यहाँ पर तो cast कर लिया, you have casted them together. तो लेकिन आप कितना पोर्शन एक्सपेक्ट कर रहे हो कि वो इसके साथ इकट्ठे बिहेव करेगा इस बीम के साथ, तो वो आप कैसे निकालोगे? सो द कोड मेंशंस may be taken as the following, but in no case greater than the breadth of the web plus the half the sum of the clear distances to the adjacent beams on either side. For T beams, this is तो टोटल आपका ब्रेड्थ ऑफ द वेब एक आएगा, सो दैट्स BW plus half of the sum of the clear distances to the adjacent beams on either side. अगर दोनों साइड से बीम्स और भी है, like अगर कंडीशन ऐसे है, if you have continuous system और ये ऊपर स्लैब है, तो either it would be a case like this, breadth of web here of this beam plus जो ये डिस्टेंस है, ये कितनी डिस्टेंस है, दिस वुड बी, फॉर एग्जांपल दिस इज say L1, then there is another distance on this side. This is L2, then this would be half of L1 plus L2. ओके, इसका आधा एंड इसका आधा, तो ये पोर्शन फिर इफेक्टिव फ्लैंज विड्थ बनेगी इफ यू देयर आर बीम्स ऑन बोथ द साइड्स, or otherwise you would have T beam ki effective width would be taken from this. What is this? BF is L naught by 6 plus BW. BW you know is the width of the web. DF is the depth of the flange. This is DF. You know this from this portion up till this portion. So I'd put it like this, ki let me copy this and then so your L naught first is the distance between points of zero moments in the beam. Now you would say, what are the points of zero moments in the beam? When we are talking about beam at the center, it means that this is a continuous beam. There is a beam here, there would be a beam here. Let's say there are three supports in this beam. अब जो सेंटर वाली बीम होगी, दिस विल बी अ टी बीम. This is your T beam here, and the slab is supported on this beam. You can say the slab is supported at this beam, or it's continuous over this beam. Uh, do you take it as a support? First of all, anyone who can answer? Do you take beam as a support? Yes, anyone? Is beam a support, or is column or wall a support? किसी के पास आंसर नहीं है? Can you take beam as a support? Sabhi, so I will ask anyone. So I think maths, I will pick up and choose anyone. And Zakir, 38.
Yes, sir.
Can you, जब आप मैं कह रहा हूँ कि there is a beam here like this. Let me show you. You have कहाँ थे? Okay, let's see. जब मैं यहाँ पर आपको ऐसे दिखा रहा हूँ कि there is a beam somewhat like this, then you have another beam like this, और ऊपर एक स्लैब है. अब इस बीम को आप सपोर्ट कहोगे? दिस बीम?
सर स्लैब के लिए हमें इस बीम को कंसीडर कर सकते हैं सपोर्ट.
स्लैब के लिए सपोर्ट कंसीडर कर सकते हो. एनीवन
जी
एल्स
सर.
हु डिसएग्रीज? सपोर्ट किसे कहते हैं?
Sir, beams are used to transfer loads.
वो यहाँ पर कहाँ ये ट्रांसफर करेगा लोड? इज दिस बीम अ सपोर्ट? इसके नीचे कॉलम यहाँ पर तो नहीं है. विल देयर बी अ कॉलम अंडर दिस बीम? शुड देयर बी अ कॉलम अंडर दिस बीम? Have you seen something like this? Let me show you.
So beam only resists load, while his columns and walls transfer the load to ground or other.
Yes. Now, what would you say? Is this acting as a support then?
No, sir.
It's not acting as a support. Okay. लेकिन अगर मैं आपको कहूँ कि दिस इज, मैं ये जो साइड में दिस फिगर इज देयर इज अ फिगर गिवन हियर. दिस इज टी बीम. ओके, आप यहाँ नजर आ रहा है? एरो नजर आ रहा है सबको? Is the arrow visible?
Yes, sir. Yes, sir.
Yes, sir.
Okay, this is T beam. Okay, so this T beam is running parallelly with the slab. लेकिन आप देख रहे हो कि there is, ये बीम तो किसी पे लोड ट्रांसफर करेगा ना at some location. So there is a column somewhere. Okay, even if there is no column at the center, there could be a column at the end here, or at that end, or there could be a wall. So that T beam is actually also acting as a support. So you cannot, you have to take it that it is supported. That's why I'm showing you कि ये यहाँ पर भी supported है, although it may not be supported at the same point, लेकिन ये T beam फिर किसी support पे load transfer कर रहा है, so it becomes as a support. Then there is a support at the other two ends as well from the L beams, right? Then your what is L naught now? Now what would be the moment behavior of this? It would behave somewhat like this. Isn't it? ऐसे ही movements होंगे ना? So the portion about the central support, that would not go in hogging, it would go in, this portion would go in sagging.
Sir, hogging.
Huh?
Hogging में हो जाएगा.
Yes. The central portion would go in sagging and this portion would go in hogging. The point above this beam would go in hogging. Thereby, there is always a distance, ye L naught, between points of zero moments in the beam. So there is a zero moment somewhere here, for example. There is another zero moment. So ye L naught hai. This is your L naught. Then your BW, you already know, DF, you already know. B is the actual width of the flange. And effective width of the flange is BF. Now, then your BF is L naught by 6, L naught, which I showed you, plus BW. But how does it take it as L naught? I don't think it takes it like this when you have, just a minute. Let me check the code again. Yes, the code mentions this. For continuous beams and frames, L naught may be assumed as 0.7 times the effective span. L naught may be assumed as 0.7 times the effective span. So you can just assume that L naught is 0.7 times the effective span of the beam. Now, which of the beams? I think it's the larger beam that you have to take, and then you will get the distance between the points of the zero moments. So it's actually taking for a continuous beam, and it's considering this as L naught, not this. Zero moment is from here up till this point. तो इसको L naught consider किया जा रहा है, not this. I'm sorry, this is not, it's not taken as L naught, but there will be two L naughts. There will be L naught on this side as well. So you will take the larger one as the L naught, the distance between the points of the